But what we're first going to do is take a little bit of a deeper dive with Professor Matthew Adams from NJIT into what is low carbon concrete and what are the sort of dynamics between options. What if you really wanted to say, I want to do low carbon concrete, what might that actually look like? So I'm just going to introduce Professor Adams. Professor Adams is an assistant professor of civil engineering at the New Jersey Institute of Technology. And he's also the Richard P. Nathan Public Policy Fellow at the Rockefeller Institute of Government, which is part of the State University of New York. He received his Ph.D. in civil engineering in 2015 from Oregon State University. Before that, he worked as a structural engineer in Cambridge, Massachusetts. Dr. Adams is a fellow of the American Concrete Institute, where he is the incoming chairman of the Committee on Concrete with Recycled Materials. And as part of his academic research, he examines the impact of waste materials when used in concrete, and he has particularly focused on using alternative cements and recycled concretes as aggregates in new concrete. So really excited to have somebody of Professor Adams' caliber and expertise is going to run us through in a bit of a deeper dive here with low embodied carbon concrete. Professor Adams, are you able to share? Let me stop my screen share. Let me know if you can
do it.
Excellent.
All right, you can see everything?
I can now. Perfect.
Great. Thanks. Okay, so thanks for having me here. It's always fun to talk about concrete and how we can get to lower embodied carbon in concrete, which is, a major driving force in the research community that looks at concrete. But first, I want to talk a bit about how concrete is like a cookie, right? So everybody is familiar with cookies. We've probably all made them at some point in time. We've definitely eaten them. And what goes into your basic chocolate chip cookie, right? You've got eggs, flour, and butter, sugar and chocolate chips, and some other ingredients to help the system. So your eggs, flour, and butter are your glue or binder. Sugar and chocolate chips are your filler and flavor. And these other items are your modifiers to help improve, the way they feel, the rise in them, just modify everything. Concrete is basically the same. We have a glue and binder system in our cement and water. We have filler and flavor in our sand and gravel. Really the goal of having sand and gravel in concrete is to reduce the amount of cement we need. It fills in the space to lower the cost and lower the embodied carbon naturally of concrete. And then we have chemical admixtures that we mix in to try to improve all of the different properties. And like a cookie, you have sort of your basic version, but then you can change a lot of the aspects to get a multitude of types of cookies. You can have a multitude of types of concrete based off of what ingredients you use. So you can change the type of flour that you might be using. You can change the type of fat that you might be using in your cookies. These are all going to change the taste, the flavor, the texture of the cookie a little bit. And similarly, in concrete, you can do the same thing. And what you use to change that is going to impact your final properties. And so all of those final properties can be good or they can be bad, depending on how you use those changed ingredients. So now that we've talked about how concrete is a cookie, what is concrete? Chris, of course, gave us a basic overview of the components, though I always like to harp that there's air in there. That's the fifth component that everybody always forgets about. But really, it's air, hydraulic cement, which for most purposes we use Portland cement, water, and then sand and gravel. And as Chris said, this is really a local material. Not only do we mix all of these components locally, but we produce almost all of these components generally within a 500-mile radius. Sometimes we're importing the cement from further away, but we're certainly not importing our aggregates from far away. Considering the amount of them that we use, that would just be very cost prohibitive. But this, similar to the chocolate chip cookie, is just your basic mixture. There are lots of things that we can add to it. We can change the type of cement that we use. We can even change out or mix the cement with other additives that will change or alter the properties or that have lower embodied carbon. We can use different types of sand and gravel in that system. There's lots of recycled materials available that we can replace aggregates with. We have our chemical admixtures that allow us to speed up the process, slow down the process, make it a little bit more fluid, add more air to the system. All of these things are changes that we're familiar with in the concrete industry to help us achieve our final properties. And for most of the time that we've been using these, we focus on these to either reduce cost or to improve our structural carrying capacity or our long-term durability capacity. But what's interesting is a lot of what we already use can be used to make quote unquote green cement or green concrete. And green concrete, of course, it could just be green concrete, but what we're really talking about is lower embodied carbon concrete. And so what's great is that we're familiar with a lot of things that we already use that will help us lower the embodied carbon. But we also have some newer technologies that are coming up that we'll talk about. So where does all of our embodied carbon come from? Concrete is responsible for about 8% of the total CO2. Most of that, as Chris said, is coming from the cement industry. But why? How come concrete has so much embodied CO2? Well, the main reason is really that it's produced at such a massive scale. In terms of per kilogram unit, concrete has a fairly low embodied carbon compared to other traditional construction materials. But we make so much of it. We make almost 2 cubic yards per person per year for every person in the world. So you can imagine that is just really unfathomable amounts of concrete that we cast every year. And so because we cast so much of it, even though it has a relatively low embodied carbon compared to other materials, the impact is very, very large. So within concrete, where is that embodied carbon? Most of it is coming from the cement production. So there's some of it, about less than or about 10% comes from quarrying the raw materials, grinding those materials, and mixing them together. 40% comes from what we call thermal emissions, so heating up the raw materials so that we can form cement. But more than 50% come from what we call process emissions. And so process emissions are part of the chemical reaction that happens when we make cement that causes CO2 to be formed. And that's something that we really can't reduce. So let's take a look at what happens when we make cement. So we make cement by taking raw materials, mostly ground limestone and clay. We put it into a large rotating kiln. This kiln is about the length of a football field, of an American football field. And it slowly turns, and as the cement moves down that kiln, it heats up. So we're heating that clinker up to about 1400 degrees Celsius. And that is our thermal emissions. We need to fuel that heat. It takes coal, oil, gas. Those are our traditional fuels. But we've done a lot of work in the cement industry to reduce the amount of emissions that come from that by using alternative fuel sources. So we use a lot of waste fuel sources or lower carbon emitting sources. We've also done a lot of work to make this process a lot more efficient over time. And as Chris said, now they're working on ways to capture carbon that's produced from this system. But most of the CO2, 50%, comes from this process that we call calcination. So CaCO3 is limestone. That's the chemical formula for limestone. When we heat up limestone, it breaks down into calcium oxide and carbon dioxide. And that carbon dioxide just turns into a gas and it off-gases out of the flume. And so that's why we get so much CO2 when we produce cement, because we're actually off-gassing it from the limestone that we're using to make the cement. And we need that calcium oxide as a major component of the Portland cement. And now, as Chris said, there's also activity to try to capture this carbon dioxide that's coming out of the kiln. And this is sort of up and coming technology. But one of the best ways that we can reduce the embodied carbon in concrete is to reduce the amount of this cement that we use. If we don't use as much, we don't produce as much, and therefore we don't produce as much CO2. Where else is our CO2 coming from in concrete? Well, we have to mine the raw materials. That takes quite a bit of energy. We have to grind down the cement. We need to mine and crush and mix the aggregates appropriately. And then there's a lot of transportation. These materials are quite heavy, and so there's a lot of CO2 bound up in the transportation of these materials, which is why it's important to use local materials as much as possible. But really, these sources combined are relatively minor compared to how much CO2 is produced just in making the Portland cement. So how can we go about and reduce the embodied carbon in our cement or in our concrete and create a nice green concrete? Well, let's look at the different materials that we have. First, focusing on our hydraulic cement. Most of our hydraulic cement that we use is Portland cement. It's named Portland cement because it looks the same color gray as the cliffs on the Isle of Portland in England, not because it was created in one of the Portlands. But this is the most common cement that's around. It's about 90% of the cement used in the concrete market is Portland cement. We do have alternative hydraulic cement. So when we say a hydraulic cement, we mean something that reacts with water to form a binder. We have things like calcium aluminate cement and calcium sulfoaluminate cements. These are used pretty readily. And we have things like magnesium phosphate cement and geopolymer cements, which are kind of up and coming. So what about using these types of cements? Well, the calcium aluminate cement and sulfoaluminate cement, they're pretty widely used, but they're really made for specific uses. They tend to have high early strengths, they set very quickly, and so they're very good for rapid repair. Calcium aluminates are used quite a bit in what we call the building chemistry market. So that's like grouts and things like that we use to place tiles. But these are relatively expensive. We're talking on the order of 5 to 10 times as much as Portland cement. They do have lower embodied carbon than Portland cement, particularly calcium sulfoaluminates have a significantly lower embodied carbon, but the cost offset and the difficulty in using them because they set so quickly tend to prevent us from using them at a very wide scale, the same scale that we might use Portland cement. Magnesium phosphate cements are still up and coming, and we're still learning a lot about them, as well as geopolymers. I would say geopolymers are more close to being used more readily, and they're great because geopolymers are made from basically waste materials, and they have very low embodied carbon. But what's difficult with these is that there's a limited availability of these, and they both require special training for use. They don't work exactly the same as we would use a Portland cement. And so it kind of will create a new educational need in the market. So let's look at something other than cement. If we, instead of looking at our cement content as just hydraulic cement, and we think of it as cementitious materials, we can start to look at other materials that don't behave on their own like a hydraulic cement, but help to boost and support what a hydraulic cement does. So these are materials that we commonly refer to as supplementary cementitious materials, and they work very closely with the Portland cement to create actually usually an improved product. And these are materials that have been used for many years successfully in the industry, but also help lower our embodied carbon. And we haven't really been taking advantage of them as a lower embodied carbon tool as much as we have used them for improving our properties. So these include ground limestone, fly ash, slag, and silica fume. And then newer SCMs that are coming up are ground glass pozzolan and calcined clays. These have a pretty moderate cost, similar to Portland cement, depending on the particular SCM. And like I said, they're really good because they're heavily used already. Most agencies, most concrete plants have some SCM available for you already. So what are these different ones? Ground limestone is typically sold as Portland limestone cement or PLC cement. The limestone replaces about 12% of the Portland cement. It doesn't impact the strength or durability. You get the same properties. Currently, it's not super available in the US, but it's being made heavily in Canada. And I think, you know, soon we're going to start seeing an increase in the production of Portland limestone cement here in the US as demand increases for lowering the embodied carbon. This new building in Philadelphia, the Drexel Academic Tower, was just made with Portland limestone cement, very good quality product. Other common SCMs, fly ash and slag. Fly ash is a byproduct of coal burning. Slag is a byproduct of steel making. Both can be used at replacements ranging up to 60 to 70% of the cement. So you can get really high replacement levels and really reduce your low embodied carbon. They're readily available. They really improve our long-term concrete properties. They give us higher strength in the end, better durability. But the difficulty with them is that they slow down our early strength gains. So you would need to either offset that or change the way that you are casting, maybe give yourself a little bit more time for the concrete to cure. Another SCM that we, this is the next slide. So we can offset those slow strength gains by using some high early strength cement, so a type 3, use some accelerating admixtures, or like I said, working with your contractors to modify your specifications to allow for a bit of a slower set. Another common SCM is silica fume. This is a byproduct of the silicon chip making industry. This we can use at a much lower replacement level, only really up to about 8%. We see a very significant improvement in strength and reduction in permeability, so that's a durability issue. You get much better durability, but it tends to make your concrete very sticky and difficult to work with. And the material is a little bit higher cost than other SCMs. And so this works great in small replacement levels in combination with other SCMs, but you know, is probably not your first go-to if your main goal is reducing your embodied carbon. Taking a look at some up and coming SCMs, we have ground glass pozzolan. Locally, this has become somewhat available. There's a couple of local companies that are producing this. This is basically just ground up glass that they've turned into a powder. Right now, we're using it in the 30 to 40% replacement level. It helps improve long-term durability, works similarly to fly ash in that it slows down your strength gain, and the properties that it will change depend on the type of glass that's being recycled, but the producer will know what that is and can work with you to answer those questions. The big question with this is really, it's unclear how it works with other SCMs. There's still a lot of research going on with these, but considering the local availability, this is a very good option for replacing your cement. And then the last one that's really up and coming that is not available in the US is what we call calcined clays. These also work similarly to fly ash. We use local clays, we heat them up, and they form what we call a calcined clays. In other countries, they're combining this with Portland limestone cement to create what they're calling LC3 or limestone calcined clay cements. And it's a very promising change. The reason why these are up and coming is because fly ash is starting to go away. As we burn less and less coal, we have less fly ash available to us. So calcined clays are going to come in to hopefully fill that hole in the market as things move forward. But there is a little bit more embodied carbon associated with a calcined clay because we're purposefully creating a material, we have to heat it up to about 700 degrees Celsius. So that involves a little bit more embodied carbon than just using a waste material. Another way to reduce your cement is through mixture design. So one of the key things is to work with aggregate gradation. Basically, if you think about aggregates, they come in all different sizes. And the smaller aggregates help fill the space between the larger aggregates. And so this is a particle packing question. The better we can get those particles packed together, the less cement we need to fill in those spaces. So working with the aggregate producers to create a better graded aggregate that increases that particle packing can help you reduce your cement content without strength loss. This does increase the cost of your aggregates, and not all aggregate producers are ready to do this and develop this, but this is something that's hopefully coming up in the near future. And then one thing that Chris alluded to is incorporating CO2 into the mixture. So this is something like what Carbon Cure and Solidia are doing. What Carbon Cure is doing, and this is the one I'm going to talk about really because this is the one that is locally available for ready mixed concrete. Generally, you're actually putting very little CO2 directly into the concrete, about 1% by mass of the cement. So if you add 100 pounds of cement, you're adding 1 pound of CO2. But what this does is it actually increases the strength of your system. So if you needed concrete of strength X, you could put 1% of this CO2 into the mixture. It helps form some calcium carbonates and other hydrates in the system. And then that grit gives you a stronger system so you can reduce your cement content by 10 to 20%. There's limited availability for this locally, of course, because the concrete manufacturers need to partner with groups like Carbon Cure to get that technology in their facility. But we do have it available in some places in New Jersey, and I believe there's a place in New York as well that's working on this. And so this is going to start to be used much more heavily in the near future. If we think about things other than the cement, aggregates, they really make up most of our concrete by mass. And so it's an important thing to consider. Most aggregates are produced locally, but in major cities like New York and Toronto, the local supply of aggregates is becoming scarce. We're having to go further and further away from the center of the city. And so if we can use a recycled material that's local, we reduce the total cost of carbon that's involved with transportation. And so these are something like recycled concrete aggregates. This is crushed concrete, widely available, fairly low cost, and we can easily use in replacements up to 20 to 50%. The difficulty with these is that they can be a little inconsistent in quality. And so as we continue to research them, we're learning how to qualify those a little bit better. But when we're talking about concrete like sidewalks or curbs, which aren't really structurally loaded, you really don't have any problems with using these materials. You're always getting the properties that you really need. Same goes for things like glass aggregates. So instead of crushing it down to a powder, we're just crushing it down to the size of an aggregate. Those can be used. There's some long-term durability concerns depending on the type of glass. So you need to work with the manufacturer there to make sure that they've done the right testing. And then something up and coming is manufactured mineralized carbon aggregates. So these aren't really widely available, particularly in the New York area. There's a company in Vancouver that's really been making these and pushing these. And basically what you have is you have a small rock that they then use CO2 and mix it with calcium oxide to recarbonate and form limestone, essentially, in layers around that rock. And so you create an aggregate that is itself a carbon sink. So it's taking carbon away and using that as the aggregate. Really interesting technology that hopefully will become more available in the near future. But moving away from materials, there are a couple of things that we can do to improve our embodied carbon for our concrete, and we can do these things first without really changing the overall cost or having to worry about, are these materials available? First, design for durability, right? So if you're designing something, don't think just about the strength of the concrete. Work with your contractor and your engineers to develop something that will last a long time. Make sure that you're designing something that can handle changes in use or changes in the area to last for a long time. I know a lot of sidewalks are often designed for 5 to 7 year lifespans because they expect them to have to be taken out for some other reason first. Is there a way that you can design around that so that you can have a sidewalk like this one that ends up being 100 years old? The second one is don't over design. Oftentimes we make concrete with very, very high strength that we don't need. Our sidewalks, our residential buildings, et cetera, are not the Burj Khalifa, right? We don't need 21,000 PSI for them. So make sure that you're designing for what you're actually using the concrete for. The higher strength you need your concrete, typically the more cement you need in there. And so by keeping your concrete at a lower strength to the strength that you really need, then you're not going to use the cement. Both of these will really help you have a targeted system that starts off by having less carbon. If you design for durability, then you're not replacing nearly as often, and that is the best way to not use more concrete. So thank you. That's sort of the spiel on how to make low embodied carbon. It's a very high level conversation, but there's lots of ways that we can reduce embodied carbon in concrete. And I really want to hit home that some of these are already being used extensively in concrete. We're not going out there and developing a new product or a new technology. It's already there. You just need to work with your local contractors to get what is available. But there are some new exciting technologies on the horizon despite that. And so you can make changes quickly and easily by just having the right conversations, but that's going to require communication between the engineers, contractors, and the local government. So thanks.
Excellent, Matt. Thank you so much. Really appreciate it. So just picking up on a couple of things, Matt, before we move on, one of the things that really strikes me again, just to kind of put a fine point on it, is that so many of these solutions, the integration again really happens or will happen, even the more high-tech things, in a conventional concrete plant. It really is still sort of localized at your local concrete plant. Is that fair to say?
Yeah. So, when we call concrete a local material, you're using lots of local products as well. And so concrete is not an assembly line. Every time we make it, it's a little bit different. You're using aggregates from your local quarry and everything. And so when you bring in these new materials like a fly ash, you need the concrete plant is going to make a new mixture design with that and make sure that it meets those requirements. And so a lot of them already have those mixture designs developed, and it's very simple for them to give you something that involves some of these technologies.
Just a couple of more specific questions. One thing that came up on the chat here, and you hear this often, is about fly ash because it's a coal byproduct. There's concerns about its linkages with climate change. And my understanding is, and you kind of already spoke to this, is that it's really, it's downstream of the emissions. It's already the waste product that's being used, and it's not driving the burning of coal. And in fact, we're losing it now because there's less coal being burned, or is that's kind of an economics question?
Yeah. So there is, fly ash is what comes out when you burn the coal. We collect the particulates, and so fly ash is the finest of the particulates that we collect when you burn coal. And for many, many years, fly ash was just put into landfills. But now it's being used beneficially in a number of industries, concrete probably being the largest. But it's become significantly more difficult to obtain, particularly in, say, the Northeast, because so many of our plants have switched away from coal to natural gas. And so over time, we're going to see less and less fly ash available.
Gotcha. And just two more points before I move on. You know, one other observation that if you could just sort of confirm, many of the different options that you talked about, we're not talking about one or the other or mutual exclusivity. We're talking about the possibility of, like, to use your cookie metaphor, you can add a lot of those different ingredients in, and that's probably our pathway to really driving carbon down, is not just one, but a combination of many of those off-the-shelf things, and then increasingly more of those novel new inputs. Is that fair to say?
Right, right, yeah. So, you know, particularly a lot of our SCMs we're using in what we call ternary blends. So you've got the cement and two different SCMs, and they work synergistically. So they actually help improve each other's performance. But then also combining that with some of our other ideas that we were talking about, like aggregate gradation or the CO2 mixing in concrete. These all can work together to help get you even higher along that reducing the embodied carbon.
And then just one last thing I want to hear, which I think a lot of the folks, particularly that are representing the PwCs and the engineers that work with local governments, is there's the question about the ability, the constraints that we have around using some of these options, particularly the ones that are more novel, given the DOT specifications, Department of Transportation, which a lot of local governments sort of rely on. And my understanding is that you don't need to rely on it, but the resources that are required locally to figure out if something is safe or structurally sound are a bit beyond the sort of the capacity of a lot of local governments. Is there anything there you can kind of speak to about what the rules are, I guess, around that? Or
Sure. You know, of course, where the funding of your project comes from always plays into this. But, you know, if you're solely funding a project, then you can help create the specifications for that project. So you can include these novel techniques. But a lot of folks, justifiably so, rely on the state DOT specifications because they know that they work well. And so, you know, if a town or a local government is really looking to push this, providing some of the resources to their engineers to help develop the right specifications is going to be part of that partnership to move this along.
And that is something that we aspire for at OpenAir as we get more people involved, local governments and experts, that maybe we can provide some of those resources that create a greater comfort level on the local level that'll allow them to sort of detach a little bit from the Department of Transportation. So, Matt, that was fantastic. There's literally a million other things that we could talk about, and we'll continue that conversation on the forum. So really want to thank you, Matt, and I'll give you a virtual applause.